Welcome back, everybody. This is going to be one of the most fun video lectures in our entire semester. I really love this material. It's weird and freaky and very counterintuitive and a lot of fun. So let's get started. The cardinality of a set doesn't have anything to do with baseball or St. Louis, unfortunately. Although I did color it red so that we could it would be a little bit like the Cardinals. The cardinality of a set is just the number of elements that it contains. So, for example, here's a set has the elements 0, 3, 7, and 26. It has a cardinality of 4. You just count the number of elements in there. There's 4 of them. If you look at bigger sets like the integers, remember those were whole numbers plus the negatives plus 0, right? Rational numbers, all the ways you can get fractions out of integer divided by integer, except you can't divide by 0. And of course, the real numbers, which is anything you can make out of decimals, those all have infinite cardinality. Those are infinitely big. Well, in the last lecture we talked about one-to-one correspondences, about bijections was the other word for that. That's a function which is one-to-one and onto. So you can think of that as just matching up every element in the first set with an element in the second set. It's like you take one element from A and one element from B, match those together, and there they go. And then another element from A, another element from B, and match those together. So what that tells us is if you have two sets with a bijection between them, they have the same number of elements because we've paired all of them up. That's exactly what it should mean for two sets to have the same number of elements, and we call that equinumerous, which is a weird long word, but I mean it makes sense when you think about it. Equa is the same, and numerous is how many there are. If you want to write this, and we won't write it this way very often, but if we need a way to write this, you can write A and then a little tilde and then B. So it says that A and B have the same cardinality. Roughly, it means they have the same number of elements. Although when the sets get to be infinitely large, that's more tricky and more interesting than you might think. But okay, here's a great example. So we talked about baseball a second ago. I'll switch to basketball for a second. Suppose you want to know how many games there are in the NCAA basketball tournament. Okay, this is an interesting question. Um, I'm not going to count any of the play-in games or any of that sort of stuff. Let's just go with just the 64 that actually make up the normal bracket. Okay, 64 teams. How many games there have to be? Right, well, okay. So one way to do this, maybe the most obvious way to do this, is to say, okay, there's 64 teams in the first round, so every team plays another team, so that means there's 32 games in the first round, and then 16 games in the second round, and so on. But there's a much cleverer way to do this. Right? Much cleverer way to do this. And it's this. There's a bijection between the set of losing teams that don't win the whole thing, and games in the tournament, right? Because every game produces a loser. Every loser lost some game. And because this isn't a double elimination, situation like the College World Series or something, there's a bijection between the losers, the ones who didn't win the entire thing, and the games in the tournament. How many losers are there? Obviously 63. But there's 64 teams that started, only one of them won the whole thing, so it had to be 63 games. No adding up, no nothing. Isn't that easy? When I was first learning this material years ago, the teacher I had told this story, and he said that shepherds used to use this idea because they would keep a bag in their, like attached to their belt or whatever, with a little pebble in it for every sheep. And they were may have been pre-literate and not necessarily able to even count, but they could keep track of how many sheep they had because when they gathered up their sheep at night to enter into the sheepfold, they could go, okay, sheep, there's a sheep and pull out a pebble. There's another sheep and pull out a pebble. There's another sheep and pull out a pebble. If they ended up with more pebbles than they had sheep, they knew that there was a sheep missing. Or if they had more sheep than there were pebbles, then they must have picked up one along the way somewhere. I don't know if they got hungry and they ate a pebble, ate a sheep, they would take out the pebble. And if a sheep had a baby sheep, then you go find another pebble and put into your pouch. I don't know if that's actually true or not, but it's too good a story not to keep telling it. Right? So that gives us this idea between connections, between bijections, right? Every sheep matched up with a pebble, and counting. What does it really mean to say that a set has 5 elements? It means that I can count them. So it means that I go through and I like stick a 1 on the first element, stick a 2 on the second element. Imagine like a whole bunch of post-it notes with a 1 that you stick on something, then a 2 written on the next post-it note that you stick on the next element, a 3 on another post-it note that you stick on the third element, and you keep going until you've used up all the post-it notes, and then you see how many post-it notes you used, right? And what the highest label was. So if a set has 5 elements, that really means there's a one-to-one correspondence between that set and the set 1, 2, 3, 4, 5. Okay? So, definitions now. A set's finite if it's empty, when of course it has 0 elements, or if there's some whole number n, so that there's a bijection between the set we're talking about and the set 1, 2, 3, 4, etc. up to n. In other words, it means you can count them, right? Lay out the post-it note and stick to each one. Okay, that's for finite sets. Infinite sets get much, much more interesting and much more fun. So a set's countably infinite if there's a bijection between it and the natural numbers. Okay? In other words, imagine going through and you've got a stack of infinitely many post-it notes, one for every natural number. And you go through and you just start putting out post-it notes and sticking a post-it note to each element of the set we're trying to count. And if you can do that in such a way that you use all the post-it notes and that every element in the set we're trying to count gets a post-it note, right? In other words, we've created a bijection which is and no element gets 2 post-it notes stuck on it, right? So we've created a mapping there that's 1-to-1 because no element in the set gets 2 post-it notes, and that it's onto because we've used every post-it note, right? No post-it notes are left over. Then our set is countably infinite. And then we'll often say a set's countable if it's finite or countably infinite. In fact, what we'll really more often say is if I say something like prove that such and such is countable, usually it's obvious whether it's finite or not. So if it's finite, I'll just say prove this is finite. So if I say prove something's countable, then I'm almost always going to mean prove that it's countably infinite because the finite case is pretty obvious. Okay, we need a lot of examples here, a lot of examples. So here's one. The even numbers are definitely countable, right? So I'm going to just list out the even numbers, 2, 4, 6, 8, 10, so on. So here's how I'm going to do. I'm going to grab my blue post-it note and I'm going to stick a 1 on the first number, a 2 on the second number, a 3 on the next number, and so on. And you see how you could do this, right? Clearly, I could keep going forever. I would use up all of the even numbers by sticking these post-it notes on them. I would use up all my post-it notes going through this way. So there's my bijection. Now, if I wanted to write down a formula, which I usually don't, but if I wanted to write down a formula, there's an obvious one, right? To get from the numbers on top to the numbers on the bottom, you just do like x divided by 2. Or the other way, to go from the blue numbers on the bottom to the black numbers above them, that's just 2x. That's my bijection. So, okay, awesome. That is a formula. We could write that down. We could prove that that's 1-to-1 and onto. I mean, the function 2x is clearly 1-to-1 and onto. You can just go through and check with the definitions. So, awesome. All the even numbers are countable. That's a little weird, isn't it? Because we've lost all the odd numbers and we can still count the even ones. So that's one of the interesting things about what it means to be an infinite set is you can lose some of your members, still be infinitely big. In other words, you can have a set with that's countable, right? The cardinality is infinite. Throw away infinitely many of those numbers and still have an infinite countable set left over. That's just what we did with the even numbers. We threw away the countably many odd ones. Obviously, the odd ones are countable, it's the same kind of idea. And we're left with countably many left over. This is what makes this such a cool thing to think about because it's kind of counterintuitive when you start to play with infinity. Okay, what if we started our set? These are the normal natural numbers, except I've just started it with 3. So I've thrown away 1 and 2. Well, just like I said before, you just start counting, right, with what you got. So I'll stick 1 on the first number, 2, 3, 4, 5, and so on. There's obviously a bijection here. It's like, n plus 2 or n minus 2, which depends on which way you're going, from the black numbers to the blue numbers or vice versa. Again, I don't really care about the formula, and I don't have to use that formula. There's lots of bijections. I could switch which number if I sent 4 to 5 and 3 to 6, and I just switched these two blue numbers around in the middle, that'd still work, right? That'd be a different bijection. There'll be more than one way of laying out the post-it notes. But the point is, I can go through and lay post-it notes 1, 2, 3, 4, 5 on each element of my set. So of course, my set, which is the natural numbers minus 1 and 2, it's also countable. So it's a fairly obvious theorem that if you have a subset of a countable set, then that set's countable. Now, either that subset is finite, in which case it's definitely countable, or if the subset's infinite, it's still countably infinite. And the idea is, the proof is, you just do what we did on the last screen. You just start counting with what you got. Right? Okay, this is a much more fun example. So we're not going to throw away things from our set. Let's add some stuff to it. So remember, the natural numbers, go 1, 2, 3, 4, 5, 6, and so on. The integers include all of those, but you also get 0, and you get the negatives of all of the natural numbers. So -1, -2, -3, and so on. So how are we going to count these? Well, there's an obvious way to count them. We stick a 1 next to number 1, we stick a 2 next to number 2, a 3 next to number 3, and then you suddenly realize, oh dear, if I keep going, 4 with 4, 5 with 5, and so on, that will use up all of my natural numbers, right? That will definitely be a map which is 1 to 1, right? Depending on which way I do this, it'll be a 1 to 1 map, say from the natural numbers to the integers, but it won't be onto, because I'm missing all of those negative numbers and 0. Right? So this is a bad way to do it. Right? This doesn't work, but it points out something really, really important. Just because you can find a 1 to 1 map, right, from the natural numbers onto the set we're trying to count, it's 1 to 1. That doesn't mean, and it uses up all the natural numbers, right? It doesn't mean there's not another way to do it, which would be onto, because there is. There is a way to do this in such a way that will be onto, right? We came up with one map that wasn't. There is another map that is. Let me show you how that works. So what we do is we take our first post-it note and we stick it on 0. That's right in the middle. Then we take our next post-it note and we'll stick it on 1. Now, if we kept going and stuck the next post-it note on 2, we haven't really done anything any different, right? If we'd just be counting, same way we were before. The trick is we stick post-it note number 3 on -1. So then we can bounce back and forth between the left side and the right side. So post-it note number 4 goes on number 2. Post-it note number 5 goes to -2. Then we get +3, then we put a post-it note on -3. Now, trying to write down that function is not that awful, but it's piecewise and it's nasty and nobody cares, right? The important thing is how the pattern works, and you can see that clearly this will give us a bijection if we do this. So in the homework, there's a note that I say that said, don't worry about trying to write out a formula necessary for some of these problems. Just explain how it works. That's what I mean. You can just sort of draw out how the pattern has to work, and it's obvious what the bijection is. There's also some homework problems, of course, where you write out the bijection as a formula, and you have to actually do some algebra to work with those, and they'll be clear in the homework which of those you're supposed to do. Okay, suppose you have two countable sets. Then the union is countable. Right? That's kind of what we got from the last example. The positive integers are clearly countable because, you know, you just start matching up 1 with 1 and 2 with 2 and so on. The negative integers are also clearly countable because I can match up 1 with -1, 2 with -2, 3 with -3. When you put them together and even throw in 0, that's a third set, right? The union of all those is countable. In fact, the real theorem is that if you have countably many countable sets, the union will still be countable. Right? So I could union together countably many sets and the union will still be countable. Right? The idea is, and you go through bouncing from one set to the other, back and forth and back and forth, and working your way through them as you put your post-it notes on there to count them. Here's another awesome example. So the set of ordered pairs of integers is countable. In other words, n cross n, Cartesian product n cross n. And we can draw that, if we draw in a grid, right, where the lines, the spacing there, the lines are 1 unit apart. So each of the lines cross at integer coordinates like 1 1 or 3 4 or 7 -2 or something, right? And all of them are represented by crossing points of these lines on the grid. So all these ordered pairs of integers are really just spots on my grid there. So I'm just going to go through and count places on the grid. And you're okay. How do I do that, right? In fact, it's maybe worth pausing for a second to think about how you do that because it's not exactly obvious. And if you start trying to do it, then there's lots of wrong answers, right? Like I could start ticking out post-it note number one and then keep going to the right, and count one, two, three, four, like we did on our first try at counting the integers. Or I could try bouncing back and forth, but then that doesn't get the things above and below it either. So, again, if you have a second, pause the video and play with it, see if you can figure it out. Okay, are you back? Or just didn't pause the video at all? Either way, it's okay. Let me give you the answer. So, the trick is to make a spiral. So, we put our first post it note on 0, 0. I put 0 there, of course, that's the origin, right? 0, 0. Then I stick my next post it note on, what is that, 1, comma 0, then 1, comma 1, then what's that, 0, comma 1, and so on. And the idea is I just keep going around my grid in a spiral, right? And it's obvious that as I keep going, that will eventually count all of my points on the grid. I will have a one-to-one correspondence because every um, point on the grid is going to get one post-it note. Every post-it note is going to get used. Okay, I'll use up all infinitely many of them. This is going to be one to one and on to, there's my bijection. And again, trying to write out a formula for that would just be a nightmare. I don't care what the formula is. The idea, though, is good enough. And as you draw out the spiral and explain how this works, that's plenty enough of a proof for this. So the theorem in general is if you have two countable sets, then when you take, say, S and T, when you take S cross T, that will also be countable. Right? Okay. What about the rational numbers? Remember, we have this these special symbols for all the various different kinds of numbers. There was n for the natural numbers that shows up here because that's the set where we get our post-it notes from when we're doing our counting. There were integers were z. Then next comes q for the rational numbers. As rational numbers, remember those were fractions. And I've still left my grid up here because here's the way this works. You can start counting out fractions. Remember, when I say a fraction, I mean an integer divided by an integer as long as the denominator isn't 0. Like 3 over 2 is a perfectly good rational number. But 17.9476 divided by pi, right? Even though you might call that a fraction because it's one number divided by another number, that doesn't count because those aren't integer divided by integer. Okay. Okay. So what we really are going to do here is figure out a way to make Q be a subset of Z cross Z because I'm going to match up every rational number, say x over y, with a coordinate point, x comma y, where this makes sense. Now, what does it mean by making sense? Well, first off, we can't divide by 0, but also rational numbers are trickier because 1 over 1, right, is just 1. That's actually the same rational number as 2 over 2 or 3 over 3 or 4 over 4. So what we'll do is we'll just keep going around counting, and when we realize that we've already used a rational number, then we just don't put a post-it note there. So in other words, we get to 0. 0 comma 0. Well, that's not a rational number because 0 divided by 0 is not a rational number, so I don't put a post-it note at the origin. Then I move over to 1 comma 0. Well, there's a problem here too because 1 over 0, if I think of it as a rational number, that doesn't count because I'd be dividing by 0. In fact, everything along the x-axis I'd be dividing by 0, so those don't get post-it notes. So the first place that actually gets a post-it note is 1 comma 1, because that if I think of it as a rational number as 1 over 1, that's 1. That's a perfectly good rational number. Ding, you get a post-it note. Now, if I move over to the next spot, this is 0 comma 1, right? Well, 0 comma 1, that's okay as a perfectly good rational number, right? 0, I can't divide by 0, but 0 divided by 1 is fine. That's just 0. So there we go. I count that one. I stick a post-it note on that grid point. Okay, so now we move over to the next grid point, making our spiral. That would be the point -1 comma 1. So if we turn that into a rational number the way we've been doing it, x coordinate over y coordinate, that would be -1 divided by 1. So that turns out to be just -1 if we simplify it. That's a rational number. That's not one we've encountered before, so we can count that one. We stick a post-it note on that one. Keep going on the spiral. We get down to the x-axis again. Well, okay, y is going to be 0 here, so we'd be dividing by 0. So that one doesn't count. When we get down to -1, -1, oh, well, that'd make a rational number -1 over -1, which is 1. We can't count that one because we've already used 1, 1 to make a 1. So, unfortunately, that dot's not going to get used, and we have to keep going. So, you see that as you keep moving around the spiral, lots of times you'll have um, to skip points because they don't make sense as a rational number. But as you keep going, you'll actually hit all the rational numbers because every rational number looks like a integer divided by an integer. It's just that some of the grid points that you would make, like we said, 2, 2, 4, 4, everything on that diagonal, -1, -1, all are the same as 1, 1. And as soon as we pick one of those points to represent 1, 1, 1 over 1, then we stick our post-it note there. We don't count one of those points again. But you see, clearly, as you keep making the spiral out, we'll count all the rational numbers this way. Isn't that cool? Okay, so if you remember back to our list of um, of different kinds of numbers, after the rational numbers came the real numbers. And Cantor's theorem says, unlike every example we've had so far that seem to say this is countable, this is countable, this is countable, the real numbers aren't countable. Which may be a bit of a surprise because it seems like everything was countable so far. The real numbers are definitely not countable. The real numbers are very much bigger than the rational numbers. Okay, so how does the proof go? So I'm going to give you the idea of the proof first, and then we'll write down something that's um, it's a much more formal kind of proof. Let's suppose that I'm going to do a proof by contradiction, by the way. So how does a proof by contradiction work? We suppose that the theorem is false, and we work until we get a contradiction. So I'm going to suppose that the real numbers are countable. Right? The reason for doing it that way is that gives me something to work with. Right now I've got a supposition that the real numbers really are countable, and I can start to use that, right? Because if the real numbers were countable, there would be some sort of a correspondence. Now, again, I don't know what the correspondence is, but this is why this isn't a real proof. I'm just doing scratch work, right? Just imagining what the proof might look like. So, post-it note number 1 goes on some number with a bunch of decimals because it's a real number. You can always write any real number as a bunch of decimals. Post-it note number 2 goes on another number. Post-it note number 3 goes on another number. Post-it note number 4 goes on another number, and so on. Now, I don't know what the pattern is to any of this, but I'm assuming that there is one. There is some sort of a bijection. So I could list out the numbers this way. Now, here's where I'm going to get my contradiction. So let's look at the list that I've made up there at the front. And what I'm going to do is look at the first decimal place for the number that matches up with my blue number 1, my blue post-it note number 1. In other words, that'd be the number 3, right? So as you see on this is the first decimal place for the first number, the one that matched up with the number 1, that's a 3. So here's what I'm going to do. I'm going to pick another number which is not 3, another digit. It can be 0, 1, 2, not 3, 4, 5, 6, 7, 8, or 9. You've got all those possible choices. Just pick anything that's not a 3. Okay? And then just write down point, and then, well, you can do this at home. pick a number that's not 3, write point, and then your number, which is not 3. Okay? And what we're going to do as we go through the list here is make a number which is going to provide our contradiction. So, next step, you ready playing at home? Okay, play along with the game here. Write point on a piece of scratch paper and then pick a digit that's not 3. Okay, now I go to the next number in my list and look at its second decimal place. Okay, the second decimal digit in the second number is a 5. So, as you're playing along at home, pick a number that's not 5, a digit. It can be a 2-digit number, just a single digit, which is not 5. Write that in the second decimal place. Okay? Then go to the third number and pick a number which is different from the third digit of the third number. Right? So in this case, 7. Okay? And you see, as you go through this, you're going to end up creating a number, right, on your piece of paper, which is different from any number in the list. Because the number that you create, if you continued this process forever, which I'm not going to make you do that because the video is only so long, but if you kept going doing this, the number you write down would not match up with the blue post-it note number 1 because its first decimal place would be different. It would not match up with blue post-it note number 2 because its second decimal place would be different. It would not match up with post-it note number 3 because its third digit in the decimals would be different. Okay? In other words, the nth decimal place of the nth number will always be different than the number you've written out on your paper, which means you've created a new number which was not covered by our bijection. Oh, wait a minute, that's a problem because we assumed that this was a one-to-one correspondence. We assumed that it was onto, that every real number got a post-it note, and you just made a real number without a post-it note. There's our contradiction. Okay, so if I were going to do this more formally, a real proof, pun intended, then I'd do it this way. I'd suppose that the real numbers were countable. Then there'd be some bijection, we call it F, between the natural numbers and the real numbers, and we could write it out like this. F of 1 equals, okay, so I'm going to write capital D sub 1 to mean all the digits, whatever they are, before the decimal place. So it doesn't necessarily have to be a single digit number for capital D. It's just whatever comes before the decimal place. Then decimal place, and then D11, D12, D13, D14. Those are all the decimal digits that come after the decimal place. Now, it may be that you have a number like a half, right, where you would have 0.5. So D11 would be 5, and all those other D's after that would all be 0. That's perfectly okay. That could happen. It doesn't have to be an infinitely long decimal number, right? It could be a rational number where the digits terminate. Same thing would have to work for F2. Only what I'll do is I'll write it this way: capital D2, then a dot, then D21, D22, D23, D24. So if you've seen matrices and linear algebra, you see how I'm labeling things like you would label rows and columns in a matrix and so on. So the like D31 is the third number, right, and the first decimal place, and so on. Okay, so here's how we create our real number, which is not on the list. I'll call it M. Right? First we put 0 because I'm not going to worry about any of the stuff to the left of the decimal place. I don't really care. I just need to make a number that's different from everybody else. So I can just focus on the stuff to the right of the decimal place because who really cares? Then I go to the first number, right, F of 1, and pick a digit which is not D11, the first digit in the first for the first number. Then I go to F of 2, right? Look at that number. Pick a digit which is not the same as its second digit. I go to F of 3, the third number in my list, right? Or in my bijection, thinking this is F of 3, and pick a digit which is not the same as D33, and so on. Okay? Now, M is not in the range of our bijection because the first decimal place is different from the first decimal place for F1. The second decimal place is different from the second decimal place of F2, and so on. So my map is not on 2. Right? Okay, this is a contradiction. So the real numbers can't be countable. Right? So what this says is really important. That we have a big jump here from countable natural numbers, countable integers, countable rational numbers, suddenly the real numbers are not countable. There's a lot more real numbers than there are rational numbers, for example. Um, and this proof is a really cool trick that we've used here by looking at the diagonal. This is called Cantor's diagonalization argument. And diagonalization arguments are really an important and useful trick that we'll probably see again before we're all said and done.